Hello everyone, welcome back. We're going to start the ML in healthcare session now. Our keynote today will be presenting remotely. This is Dr. Fani Deligianni. She's the head of the healthcare theme here in computer science at the University of Glasgow. Her research interests are medical imaging computing, statistical machine learning, and human-machine interaction. Today, she will discuss AI in pervasive well-being and health. So whenever you're ready, Dr. Deligianni, over to you.
Thanks a lot for the introduction and the invitation to participate. So my talk is going to be current work we're doing in my lab on artificial intelligence in pervasive well-being and health. So let's first go to give you an overview of what pervasive well-being and health implies in this context. So we are in a transformative period with several opportunities in developing AI technology to promote independent living, to shape therapeutic interventions, and improve prognosis. The reasons for this are two. First is the availability of patient data over a decade and the ability to use those electronic health records, which they involve clinical assessments, prescriptions, blood tests, and medical images, to create risk prediction models. And subsequently is also the maturity of sensing technology, which enables new applications at patients' home, where we can use continuous monitoring of vital signs in a high precision and high frequency, either that's to record ECGs, blood pressures, or human motion data, as we're going to see subsequently. However, this comes with several challenges. One of the biggest challenges with medical data is the annotation and, in fact, the scarcity of labels. Whereas with natural images, we have million and billion of annotated data, with medical images, we have few hundred because of how difficult it is to find experts to deliver these accurate annotations. This becomes even more problematic when we have sensing data of continuous streams. Similarly, the imbalance of our data is a challenging problem, since we know that normal samples usually are far more than abnormal samples. The quality of the data, the sensory data quality, and the annotation quality should be also taken into consideration. And finally, the heterogeneity of the data, and we already spoke about different modalities, medical images, tests, text, clinical assessments. The huge heterogeneity and the domain shifts are profound in this domain. So my talk is going to be delivered in three parts, and we'll give you an idea of research we're doing with my team, my students and postdoc, in three different areas, and how these areas connect with this bigger picture on pervasive well-being and health. So first, I'm going to start about artificial intelligence with electronics health records, and this is a lot of it is collaborative work driven by clinical experts. And then I'm going to talk about AI in medical imaging, and here you're going to see a shift in a domain that we have a lot of public data set and very specific tasks, and medical imaging analysis 3. And finally, we're going to talk about new application and new areas in healthcare, in particular, the possibility of mining human motion data with artificial intelligence to improve health and our knowledge about diseases. So quickly, let's see what is electronic health records. So electronic health records encodes very heterogeneous information of the patient's history journey, which can include blood tests, vital signs, disease diagnosis, and GP visits. What we observe here is that a lot of these data are driven by the disease itself. So the more sick someone feels, the more often he will go to the doctor and the more tests he will do. And that affects the data we currently have. And here what you see also is that, and what I told you already, is our ability now to have electronic access to this data and have information coded electronically, well encoded based on the international classification of diseases system, which allow us to use this coding also within our models. So the classical way the doctors and our collaborators use to process this data from the electronic medical or health records, which is a term used interchangeably, is a pipeline which first requires a lot of experts' knowledge to define the problem. And define the problem and then understand the data and extract the related data. And subsequently, you also need expertise to choose features from the data that are relevant and develop the model as well as evaluate the model. So to give you a quick example, we looked into factors predicting all-cause mortality in patients with type 2 diabetes. And this was stratified based on the socioeconomic status of the patients. So the reason of using type 2 diabetes here is because it's more triggered by lifestyle choices. And based on our clinical expertise, we have to, our students have to devise a pipeline starting from thousands of patients, data stored in NHS, Glasgow and Clyde, exclude patients with type 1 diabetes with more a genetic disease that appears early in life, and then focus on the population on the record at hand. And based on that, prediction models are new, is not a new concept in clinical research. In fact, it's well established with statistical models like regression analysis, as well as a Cox regression. In fact, the state of the art in this research is using machine learning models such as survival, such as random survival forests, to understand the risk of a patient, in this case, to die within 10 years of follow-up. And the factors highlighted from this research is based on interpretability analysis of the models. And we can see here an example, but we should take into consideration that here clinical expertise has been used to also select the variables used in this model. Effectively, such a model performs 2 or 3% more than what a more classical statistical model will perform. However, there is far more potential with the ML than previous statistical models on the fact that you can use far more variables for your models and being able to handle better correlated variables within this context. So for this reason, we also use deep learning with electronic health records. As most of us know, the advantages of deep learning is on the fact that automatically can extract a relevant feature even from raw data. So without require expertise in the specific domain. So you can see we used a similar population, and now we look in people 50 years or more old, and that was a large population, 380,000. And we look into hundreds of variables that include demographic information, medical history, blood test, prescription, and hospital records. So one of the biggest problems is how to represent this very heterogeneous information. And naturally, you have two choices. One is to have the classical tensor and sparse matrix representation. And the other choice, which inherently encodes the complexity of this irregularity, is a language-based representation. So if we go to understand better those two representations, the sparse matrix representation will be at least a three-dimensional array tensor, where you have in one dimension the features, and the other dimension the time, and another dimension about the patients. You can imagine how sparse this would be, given the fact that a lot of patients won't have most of these features and will be only have values within a very specific time frames. On the other hand, a language representation in this context is far more natural and more compact. And here we can see an example where for one specific patient, you can encode the prescription in month 0, and then we can see that in month 1 he had a heart failure, and then there is nothing happened in month 2 and 3, and then again in month 4 he was hospitalized for anemia, and other demographic informations. So based on this representation, then it's quite common to use a language-inspired model, which we are familiar with. So they are based on attention. There's transformer-based, fine-tuned for electronic health records. So here you need to consider that you need to pre-train those models with a new vocabulary to account for this different coding system, which encodes the information in medical domain. So our outcome variable here, what we're trying to predict, it was sudden deaths. Sudden deaths are difficult to define. So very quickly here, just to mention that the definition we used are death outside the hospital or within 1 day of a hospital admission in patients who have no evidence of a terminal illness. So that's what we're trying to predict. Now, you need also to consider that we started with 380,000 patients. Effectively, though, the sample you have from those dying suddenly is very, very small. So as you see, because of the imbalance of the data, your samples size are very much restricted. And what we found is that a language representation and using the BERT model in certain cases was provided some advantages and a better performance, which in this case, compared to the classical linear regression, was almost 10% better in terms of F1 score. So that gave us promising results, but interpretability was an issue. And it was very difficult to convince the clinical doctors that our interpretability maps are reliable and reproducible. far more, it was also obvious that they were biased on the model because of the fact that you can have a prediction model based on just a number of the blood tests and not the values of the blood tests. And so this was some of the constraints and challenges we faced. So now going to my second part, I'm going to talk about the medical imaging analysis we're doing currently in my lab. And I'm going to talk briefly about the transition from CNN to transformers in state-of-the-art medical imaging analysis. And then I'm going to go more into the challenges we discussed before about how to utilize optimally both labeled and unlabeled data in order to improve and to address the lack of availability in healthcare of labeled data. So for those that they have done image segmentation, they must be familiar with the UNet architecture, which is a convolutional network. And it consists of two branches, one branch where you downsample your image and another branch you upsample your image. And in order to be able to extract high resolution maps and well delineated information about the regions of interest, you need also to have skip connections here to concatenate the output of previous layers with the input of the upsampling layers. So this was a very successful technology in AI 5 or more years ago. And then slightly we started shifting towards attention and transformers, which is a deep learning architecture inspired from natural language problems. So what we can see here is that transformers are very powerful, but they also have inductive bias, so they require more data to train, and attention by itself have high complexity as well, which implies it's very difficult to encode local information very well. So there is good reason why combining convolutions projections within the transformer architecture, it can optimize our transformers. And this is what we tried here, where we start from the swing transformer, which is basically a UNet architecture with transformer blocks, and we replace those blocks with our CST layer, and in this way we introduce more convolutional projections in order to be able to bridge this gap between the two architectures. And this paid off, and we can see here some of the results quickly. So here what we see is a Synapse, is a publicly available data set called Synapse, which contains abdominal CT scans. We see here that we have 8 organs segmented, which include aorta, and gallbladder, spleen, kidney, liver, pancreas, and stomach. And if we start from the right-hand side, we see the classical transformer in the swing UNet shape. It seems that it doesn't perform well. In fact, specific regions like the spleen is missing. And then as we introduce convolutional projections, we alleviate some of the problems posed by the linearity in the swing architecture, and it improves the performance of the model. And we also add 3x3 convolutions for feed-forward network, and finally, we show the results of our full architecture with depth-wise separable feed-forward layer. So the promising, this provided a very promising results, in the scenario of the fully supervised learning for medical image segmentation. And so after that, we looked also, we wanted to look into the semi-supervised learning. So we start looking into architectures used for semi-supervised learning, and usually those depend on a teacher-student framework. And since you don't have all the labels you need, so a teacher-student framework provides the ability to create pseudo-labels. Most of the times you have one network, the teacher, which is trained on the label data, and then it's used to generate pseudo-labels for the unlabeled data. And then the other network, which we call the student network, is trained on both the label and the pseudo-label data. And this way we can distill knowledge from one network to the other, and there is a lot of different variation on that. What we do know that is that achieving consistency in semi-supervised learning is challenging. And when we talk consistency here, we talk about the fact that the two networks need to produce similar outputs for similar inputs, even if the inputs are perturbed. And what we do know also is that the SQL network doesn't work well, performs poorly, because if you try to create pseudo-labels from a network and use those pseudo-labels for the same network, then seems to converge towards wrong direction, and perhaps it exaggerates the bias of the model. Therefore, we started looking across pseudo supervision, where actually both networks can learn from each other. And we introduce, in this context, some multi-scale cross-contrastive learning for semi-supervised framework in medical image segmentation. And this, what that framework give us the benefits of having the cross-teaching, but also have a local contrastive learning. And with this way, we have enhanced the training stability and consistency of our result, both in the output prediction, but also in the feature level, by the fact that we use a multi-scale contrastive learning framework. So understanding a bit about supervised contrastive learning. When we talk about contrastive learning, we talk about ways of learning representations by comparing similar and dissimilar examples. Here, we use supervised contrastive learning, and the similarity and dissimilarity in this context are defined by the class labels of the images. In addition to contrastive learning, we also incorporated a balanced contrastive loss. And remember of the fact that data sets in medical imaging segmentation are in balance of different classes. They appear to have very different influence and prevalence in the data set. Therefore, this needs to be normalized and for each class to enforce an unbiased representation learning in this context. So these are some of the results, and you see here on the right-hand side, you see again the synapse data set, which we talked before. You see the ground truth as well as our own methodology and a baseline. On the left-hand side, you see the ACTC data set, which is cardiac MRI images from 100 cases with which effectively we want here to identify the right ventricle, the left ventricle, and the myocardium. So in the context of semi-supervised learning, it's important to show how the semi-supervised learning performs under different percentages of label availability. So we see here how well our method performs with 10% and then with 5%, and as well as just one case label data. There is a gap between supervised learning and semi-supervised learning, and closing this gap is very important in order to be able to use those methods in practice. Another contribution of our work has been done by looking into the certainty of the networks. The certainty of the networks here, it was just encoded on the logit space of the output of those models. Although this is not very accurate, in certain cases, it allowed us to extract negative features for our contrastive learning framework. I'll try to explain that better. So in some cases, by looking into the probabilities of those class samples, you can tell very easily whether a sample belongs to, in this case, to myocardium. In some other cases, you might not be able, by looking the probability maps, to tell whether it belongs to myocardium or to the left ventricle. But you can say with a certainty that it doesn't belong, for example, to the background. And this can help us to actually create negative samples, therefore improve the variability of our existing samples and improve the quality of the samples we have, and use those samples within our contrastive learning framework. So this is ongoing work. And now I'm gonna jump into the human motion analysis part of my talk, which connects more with research and efforts to collect data and biomarkers from patients at home, and take into consideration the limitations at this setting. So human motion analysis, for those that are not familiar, most people, they know how important human motion analysis are with sports and orthopedics, and how important it is also to predict falls in older people. It is less known that human motion analysis can help identify frail people and can help also to track the progression of their frailty. And also is an important biomarker for neurological diseases as well as mental disorders. So we started looking into human pose estimation, and human pose estimation is the first step before any type of human motion analysis. And the quality of the human analysis, it is restricted by the quality of the human pose estimation. So we thought that it's difficult to make a reliable human motion analysis if our data and the information we have from the original data is not extracted well. And we look again into a teacher-student architectures, but within the context of knowledge distillation. So here we have fully supervised networks. And our goal is to produce smaller, more compact networks with high throughput that we're able to deploy to smaller devices, which are usually the devices people have at home, which can be mobile devices or other edge devices. So what we see here, at the bottom, you see a teacher network, but effectively is a teacher heat map network. So what it consists, so you get the input image, and then you have a backbone image. And this typically is an HR network, so it's a convolutional network, which is very important in order to extract features. And then you have a classical transformer with a linear projection and attention layers. So why teacher heatmap network? So when we're looking into the heatmap based methods, what we know is that they generate Gaussian heatmaps for each joint. In this representation, each pixel intensity indicates the likelihood to have present a joint. So these methods therefore require to decode the heat maps back to key points, and they normally are trained with mean square error between predicted and ground truth heat maps. So their performance is quite high. And the other option we have is to have a student regression network. To have a regression network for human pose estimation. And a regression network, part of it is very similar to our heatmap network. It only differs at the end part, where now you don't have the Gaussian heatmap generation, but in fact, you use regression-based method to predict joint coordinates directly. Therefore, you don't need anymore to decode the key point joints, and this is fully end-to-end trainable approach. So the advantage of the regression networks is usually that they're more lightweight than heatmap networks, but they don't perform as well as heatmap networks. And that was the reason why we use here as a teacher the heatmap network, trying to distill knowledge, was basically use a student regression model to distill from a heatmap teacher model. You see here various laws defined. So we see here the laws, the mean square error between the key point tokens of the teacher and the student model. The key point token laws. We see also the visual token laws. So this is in the feature level, and then we see also losses directly from the output of the networks. Again, these are mean square error loss between the simulated heat maps from the student model and the teacher heat map. Integrated overall joints. We see also the confidence scores regress from the student model and calculated against the peak score of the teacher heat map. And finally, we see a loss which represents a mean square error between the predicted key points from the student model and the ground truth. So our main contribution here was to change the transformer layers and try to make them more efficient by introducing global filter layers. The idea on the high level is very simple, and it's based on the fact that if you use the frequency transform of the signal, then the convolutions become multiplications in the frequency domain, and then this reduces the complexity of the operations and improves the efficiency of the network. And we devised two weighting strategies. So one weight strategy is where you had a global filter, and you just transform your input signal with fast Fourier, and you multiply by this global filter. Or you have a more dynamic weighting approach where you can fine-tune each of the pixels weight. So now, if you see that architecture, you see on top again is the same teacher heat map network we saw before. Now on the bottom is our new student pipeline, where we have our global filter approach or a dynamic filter approach to perform attention. And what we see here on the right-hand side was also that we experiment with coordinate classification. So we noticed that transforming the regression problem to a classification problem improved a lot the result, regardless of whether we use distillation or not. Therefore, by binning our output, we were able to use coordinate classification to enhance the performance. So let's see how the results look and try to understand how the different parameters affects our network. So you see our model here, which is either our FFT approach or the more classical attention approach. And then we see the backbone. I talked to you before. We have a medium-sized HRNet or an HRNet, a larger HRNet W48. We see here the weighting, whether we use a global filter or whether we use the dynamic filter. And when we don't have a backbone, we see that the dynamic filter performs much better than the global filter because it's easier to fine-tune it and it's easier to extract relevant feature representations. However, it still has a big gap between the performance and the state of the art. Therefore, we kept the backbone in and we tested again with the global filter and with the dynamic version. And we found that using a global layer, that was a good compromise between number of parameters and performance of the network. And this is a bit more comprehensive results, and our approach, in particularly introducing global layers within the transformer, can apply both for the regression models and the coordinate classification models, since this only changes the first part of the model. What we notice is that if we introduce the global layers within the regression models, then the distillation works very well. So we have, if I remember well, more than 10% improvement by applying the knowledge distillation. The coordinate classification models, we have some improvement, but not as much we get with the regression models. And this is because the coordinate classification models already perform very well. So go here and I'll show you some qualitative result from our approach. So we see at the bottom the ground truth, then we see the attention based approach based on regression, and you see our approach regression based, but based on our FFT global filters, and then you see also attention based with coordinate classification and our approach with coordinate classification. And the message here is you can get high quality results similar to state of the art with less parameters and much better throughput. Here we see some preliminary results to showcase that it's easy to fine-tune those models even if you have a domain shift, they can still perform reasonably well even with a few data sets. But I'll go now to the last part, which is about privacy preservation in human motion analysis, and trying to understand the complexity of this field. So the first thing that would like to discuss is what we see here is microdoppler spectrograms of a person performing 3 different activities: walking, picking up an object, and drinking from a cup. What perhaps people they don't realize is that even modalities that we are assumed they are privacy preserved, or perhaps we cannot recognize the subject by looking the raw data. Nevertheless, they have features that they can reveal the identity of the subject. If you build a classifier, the performance actually of this classifier in recognizing the subjects is quite high. And the other concept that we need to discuss with relation to privacy preservation in computer vision is that it has a different approach to achieve different goals. So, for example, we know that deep learning models, they are very well at memorizing data set, specific samples from our data sets. And therefore, we want to create models that are privacy preserved in order to be able to share the models themselves between our users. But in computer vision in particular, privacy preservation is also related to the anonymization of the data themselves to protect the subject information. In both cases, as we're going to see, there is a trade-off between utility of the data and models and privacy. So here, for our data set, we tried specific threat models in order not only to understand the computer vision and the performance of the model, but also to understand the security threats and how sensitive these approaches are to the security threats that are very common in the field of security and privacy preservation. And we started with the membership inference attacks, which are simple attacks, black box attacks, where people, they don't have access to the model themselves, but they do have access to the output of the model, and they try to infer information from the output of the model with relation to the input data. So the reason we're starting with these baseline models is because they are used as a base in more elaborate attacks and more advanced attacks, as well as adversarial attacks against models themselves. So we wanted to explore here differential privacy in the context of data anonymization in our case. And differential privacy is a very common concept in privacy preservation. In what it does, it is inject structured noise in our data based on a parameter we call epsilon, based on epsilon and delta. Here we look into epsilon, and the smaller the epsilon is, the more noise it is injected. Therefore, there is a compromise between the privacy preservation as this is observed by the epsilon parameter and the accuracy of the utility of the models developed based on the data which have been which we incorporate noise in. In this case, to improve the utility of our approach, we look also into attributions. Attributions are methods where they try to identify which pixels on the image they contribute more to the decision of the model. So we are driven here by the fact that if we preserve more the features that are related to our task at hand and not to the subject identity, then in this way we can improve the utility of our model while we achieve high privacy. And I'll give you only, this is also ongoing work, has been submitted. I'll give you a couple of examples of our results. So on the table on the left, what I show you is the performance under black box membership inference attacks using 3 shadow models. So membership inference attacks, as we said before, they aim to identify whether a sample belongs to the training or not of the original model. And they can do that by developing new models, shadow models, which are classifiers, which they use the output of the original model to build classifiers to give you extra information about the model at hand. So when we talk here about baseline, we talk about a model without any privacy preservation, and we talk about the clean test accuracy, which is the accuracy we try to maximize. And then we also have now the accuracy, precision, and recall parameters from the attack model that we try to eliminate. We used a number of different baselines, and I'll go quickly on that. The optics one is a data anonymization technique that has been developed for data from cameras, and it is a hardware driven. So the idea is that you have a mask that you can use, a trainable mask that will sit on the hardware side, and that will filter the private and the sensitive information by injecting noise. It can achieve high privacy preservation, but it compromises a lot the utility of the models. And then we have a number of attributions we tried. And we tried the well-known GradCam, and we tried science methods, and then we also wanted to focus on more state-of-the-art integrated decision gradient methods, and to see whether we can achieve better utility and at a reasonable privacy preservation values. And then what you see on the right-hand side, again, is another attack under the hop, skip, jump attack, which is an adversarial attack here. That it does not only try to infer the membership here, but in fact, it attacks the model by synthesizing data and trying to confuse the ability of the model to classify well the data at hand. So, and we see that our approach with the integrated decision gradient thresholding, it improved the utility of the model, and also it was more immune to adversarial attacks. So taking, I guess, all this together, what we have explored and what we have emphasized here is the importance of building semi-supervised learning approaches. We saw how we can use knowledge distillation to create lightweight models to deploy at home. And we also start exploring differential privacy in terms of anonymization in human motion analysis. So I would like to thank a lot my team, my PhD students you see in the picture, and my postdoc Idris, and also a number of collaborators which they have contributed to this research. Thanks a lot. Do you have any questions?
Yes. Thank you a lot for that, Fani. Perhaps I'll start with a question. So you covered basically the role of AI here very well, but I was wondering if you had any intuition on the devices. So for example, you mentioned edge devices, or perhaps recently there's also a surge of new optical devices, sort of cheap devices that are being rolled into healthcare. Is there any standard that should be set for these devices? So taking the responsibility off the machine learning, for example?
Yes, that's a very good question, and we thought about it. We haven't done a lot of work on this side, on edge devices, or on federated learning. So we, because we, in order to understand how our models would perform on those devices, we had to simulate those environments, and there is very now few approaches of doing that and understanding better the performance of those models. But it's definitely something important for future work that we would like to try it.
Okay, thank you very much. I'll open the rest of the floor to questions. Does anyone have? Valentin over here has a question.
Hi, thanks for the talk, Fani. I'm wondering what's the current state of AI in the NHS? How open are they to implementing, for example, your vision models?
Yes, I think, well, the work we did was pioneering in the sense that there is not a lot of effort to translate this technology into NHS records in Scotland. So we started from lacking basic hardware stuff. Basically, we didn't have the hardware to perform to be capable to handle our models to start with. And we moved into to other restrictions. So to give you an idea, first of all, it has a cost to get data from Safe Haven, which is a considerable cost for early careers researchers. And even if you do that, you still lack a lot of knowledge on the clinical domain on how to clean those data and how to process and how to make sense of those data. But let's say you solve these problems, then you are restricted about the fact that all these are very regulated frameworks. So you need to have those data and analyze those data within a research environment which is secure. And there's a cost related to this environment that also is very difficult for early career researchers to be able to cover. And this was and our data set was not it didn't include medical images again, so it was only electronic health records. So yes, so we had problems in many different levels, but I think the biggest problem is on sustaining the research within our framework, within the computing science timelines. You need to have publicly available datasets or datasets that are reasonably available. And you should have these datasets and tasks, benchmark tasks already created for you. So then the research should be focused on the technology and how to build better models, whether our research was focusing on persuading people why this is important and why it's better. And I think that's very difficult to handle, along with all the other challenges you have within this research area.
Anyone else for questions? If that's everything, one more round of applause to Dr. Deligianni.